Okay, so the power rule, derivative of x to raise to some power is equal to n times x to the power minus 1. We've been using this all the time. We use it a lot. We have proved it we started with whole numbers, and then we went to integers, and then we went to rational fractions. And what we're going to do now is prove that it works for any real number. The main purpose of doing these proofs, I could just have told you the power rule and said this is it, but really what we're trying to do here is get you used to seeing these proofs and seeing what they look like. Now you may or may not be moving on and doing a lot of proofs. It just depends on what you're planning on doing for math. But I think it's useful to sort of see how these things get worked out. So let's assume that n is any real number, and I can therefore rewrite x to the n as e to the n natural log of x. Remember, e to the natural log cancels itself out. E to the natural log of x to the n, and then I can bring the n out in front, so we get e to the n times natural log of x. So let's take the derivative. And the derivative of this, again, we'll go ahead and remind ourselves that this is the outer function, this is the inner function. The outer function does not change when I take the derivative. Derivative of e to the u is e to the u times the derivative of n natural log of x. Well, n is a constant, so the n will just stay there, and natural log of x, of course, the derivative is 1 over x. So let's do a little simplification. We know that e to the n natural log of x is just x to the n, because that's where we got it from, times n times 1 over x. Simplifying x to the n over x is x to the n minus 1. Hey, look, there it is. The derivative with respect to x of x to the n. And this is true for any arbitrary. So let's just do a couple quick examples. Example 5, y equals x to the root 2. And the derivative of y with respect to x equals square root of 2 x to the root 2 minus 1. Here's another quick example. Y equals more complicated. 2 plus sine of 3x to the pi. The derivative of y with respect to x equals, now be careful, because this is your outer function and this is your inner function. So initial step here is that this is pi times 2 plus sine of 3x to the pi minus 1. And there's a temptation to do the derivative inside times the derivative of the inside, which is 3 cosine of 3x. And so there's your derivative. All right, go ahead and do exercise 35 if you are in my class. And then I'm going to come back and do one more example, so you can pause this video. Okay, let's do example 6 together. And we've got function f of x equals natural log of x minus 3. And we want to find f prime of x. Now here's where this gets interesting. We know that the function natural log of x looks like this. This is natural log of x. It has a domain x greater than 0. And we know that the natural log of x minus 3 is a transformation, and this had an intercept of 1. So this will have an intercept of 4, and it will have a domain of x greater than 3 because we now have an asymptote over here at x equals 3. So the derivative of a function can't exist outside the domain of the function. So when we find the derivative of this function, we're going to know that it doesn't exist. Now, isn't this obvious? Well, let's take the derivative and find out. F prime of x equals outer function, outer function, inner function. The derivative of the outer function is 1 over x minus 3. The derivative of the inner function is 1, so this is actually a pretty simple one. And we'd be tempted to say x is not equal to 3, and this is a true statement. This derivative does not exist when x is equal to 3. But it also doesn't exist when f of x doesn't exist. Which means that actually the derivative is 1 over x minus 3 only for values of x greater than 3. Okay, I'm so used to teaching, I was about to ask, are there any questions? But of course, you're watching a video, so that would be completely and utterly pointless. And we'll be back. Our next topic is going to be logarithmic differentiation, but I'm going to save that for the next video. All right, thanks for watching.